complex numbers lesson. Right, complex number lesson is another very easy lesson, people. Another very easy lesson. Every lesson at the very beginning, at the start of every lesson, usually you can hear this statement, very easy lesson. But finally only you realize that is too easy, no? That is too easy, right? Okay, anyway, people, this complex number lesson contains more theories. I take more number of hours to discuss this lesson, doing more sums, because every year a question is coming. This is coming under part B. Part A coming either by matrices or binomial. Okay, right. Then, of course, very easily you can score this one, and very interesting lesson in the future for your higher studies, especially in the university. When you do engineering courses, definitely you will find this complex numbers. Involving complex numbers, more lessons, more applications available, especially in electronics and electrical engineering. And when you learn physics in the future, when you specialize physics as a subject in the university, I think, not I think really, you will again come across this complex numbers. So more applications available. At the moment, if I try to explain the kind of application of this lesson, it is not easy because we don't have such knowledge to understand. But of course, remember, this lesson is so important one in the future, right? So in the complex number case, people, we are actually in the A level, we supposed to discuss the elementary fundamental theories and related questions only. Okay, right. So therefore, this is very easy one and may be confusing very easily. So therefore, we'll discuss this theories very well at the beginning. Thereafter, we can very easily go for the questions. You will find when you properly learn the theories and do one by one, step by step the questions, people, this lesson is so easy lesson, right? Okay, so then write down, people, the heading as complex numbers. Is the heading, right? There, the subheading, write down imaginary numbers. Imaginary numbers. Right, people, you know what is meant by real numbers. Real numbers means all the numbers available on the real number line. This way. Are called as real numbers. Are called as real numbers. You know, in our day-to-day mathematical works, the numbers we use are the real numbers. And you know, people, when we consider square root of 4, you know the answer of this plus or minus 2. Plus or minus 2. But when you are asked to find the square root of minus 4, people, we can't find this. We can't find this. That is, of course, called as an imaginary number. You can very clearly understand this answer, people, we can't get by the real number line. For this square root of minus 4, people, we can't find an answer which is available on the real number line. Okay, but people, this also having an answer. That answer is not available on the real number line. Even though nobody can say this does not exist. This is, people, exist in the answer of this is existing there in the set of imaginary numbers or the set of complex numbers. Actually, when we learn maths, people, so far, we learned about the real numbers. Involving real numbers only, everything we learned. That is why always we try to give an answer for this also by taking a real number from the real number line. But for this, the answer is not available on the real number line. But for this answer available in the complex numbers. Then you ask, what is that? And that is what people were supposed to learn here. So therefore, no longer we say this has no answer. This has an answer, but not real. That answer is imaginary. Now we'll search what are these imaginary numbers, and so on. People, in this case, first we have to understand what is really imaginary numbers. One example is this, people. This means, now suppose when I square this, what happens? -4, root of -4, we square. Then we know root mean power half, that to the power 2. Then this and this when you multiply, we get -4. Half and 2 is 1, no people. -4 to the power 1 is -4. Then you can very clearly understand perfect square of particular number is now minus real number. This -4 is real number, minus real number, negative real number. So then we can rewrite this one again. We have a number here. After squaring that, we get this as -4. So this is negative real number. Okay. Then people, simply we can define imaginary number as this. If the perfect square of particular number, we don't know what is that number. If the perfect square of a particular number is negative real number, then that so-called particular number is defined to be an imaginary number. Right? Imaginary number. So then the perfect square will be negative real number. You know, people, when you square real number, whether it is positive or negative, after squaring that number, our answer is, people, positive. We never get negative answer after squaring what? A real number. But in this case, after squaring a number, we get negative real number. Then that number is defined as the imaginary number. So therefore, square root of any negative real number is an imaginary number, right? So if we have something like this, negative real number here, its root, negative real number, its root is, people, an imaginary number. That is how we basically identify imaginary number. Perfect square is negative real number. Perfect square of a number is negative real number. Then that number which has been squared is defined as an imaginary number. Right? Now, after this, people, now we can come to the imaginary unit. We define something called as imaginary unit. Imaginary unit, it is, people, denoted by the notation this form. It is very similar to I. I. This is really not I, very similar to the letter I. It is a Greek letter called as the iota. But for our convenience, right, we use that as, we pronounce that as, or we call that as I. Then the imaginary unit I, iota, we define like this. Imaginary unit I is defined to be square root of I. I squared is -1. Imaginary unit I is defined to be I squared is -1. Or I is square root of -1. Right? I squared equals -1. I squared equals -1. Or taking the root, I can be subjected. I is square root of -1. That is how we define the imaginary unit I. imaginary unit I. Then you might be trying to find what is people this I, so that after squaring that, to get this answer as -1. People, they are also, if you try to find out after squaring this thing to get the answer as -1, what should be this I? You might be searching to find this. People, if you try to find this, you will try to find this answer for I by the set of real numbers. From the set of real numbers only you will try. But people, remember, in the set of real numbers, so real number line, you can't find such answer for this what I. Therefore, you might say, no, this doesn't exist. True. This doesn't exist, people, where on the real number line. Therefore, that we can't say that does not exist. That is not available in the real number line, no real number set of real numbers. But that is existing in some other set of numbers. So therefore, hereinafter, people, right, this kind of number value, this kind of value, square root of -9, we never say it does not exist. We never say that does not exist. That exists where? But not in the set of real numbers. That exists in where? In the set of imaginary numbers. Okay. So therefore, here also, people, don't go to find this value of I from the set of real numbers. It doesn't exist in the set of real numbers. So that is existing in another separate kind of set of numbers called as complex numbers. So therefore, hereinafter, people, when I say I squared is -1, then I equals square root of -1, then you have to accept this answer available. This answer available, not in the real number line, but it is in another set of numbers. Okay, so therefore, the origin of forming the imaginary numbers and complex numbers is this point, people. From this position, we can give proper definitions for the imaginary numbers and complex numbers. Okay, right. So then remember, hereinafter, whenever I write, people, I is the imaginary unit. I squared is -1, so that I is square root of -1. Right? This is existing now, not in the real number line, set of real numbers, but in another set of numbers. Right? Now, people, I told you this is an imaginary number, right? Because once you square this, the answer is negative real number. So therefore, the square root of -9 is an imaginary number. Now, I can write that square root of -9 like this. The -9 I can write, people, -1 into 9. Okay. Then this -1 I can write as I squared. Right? I squared is -1. No? Then I can separate this into 2. Root of I squared, root of 9. People, root of I squared is I. Root of 9 is, people, plus or minus 3. Then see what happens. Square root of -9, you can write as plus or minus 3i. This way I can write. Then I can write square root of -9, 3i, or minus 3i like this. Right, people? Okay. Then you can see what? The square root of -9 is an imaginary number. Is an imaginary number. Right? So then square root of -9 has two answers, 3i or minus 3i. So therefore, people, you can very clearly understand this way an imaginary number you can write in the form this. Very carefully when you study that form, people, it's this first number is real number. Second is I. Therefore, you can write any imaginary number as a product of this way a real number and the imaginary unit I. Okay, so therefore, when x is a real number, if this x is multiplied by I, okay, then this x into I product is an imaginary number. So therefore, the formation of an imaginary number, now you can understand, an imaginary number can be formed how, people? Multiplying in real number by imaginary unit. When you multiply any real number by imaginary unit, the product is, people, an imaginary number. So now, for example, if I put for this x2 and 2y is an imaginary number. Our basic idea about the imaginary number is once it is squared, we get negative real number. That is how we identify it as the imaginary numbers. Now, when I square this 2i, you can see that property. What is that, people? After squaring this 2i, we have to square this 2 as well as I square this minus 1, then we get minus 4. Squaring this 2i, we get minus real number. Therefore, this 2i should be an imaginary number. So therefore, people, imaginary number can be formed by multiplying any real number by imaginary unit, any real number. That real number can be positive or negative. Once you multiply that by I, imaginary unit, the product will be an imaginary number. Right? So therefore, in the most general form, imaginary number you can write as x into I, right? Or IEX also correct. Now let's see, people, what is meant by complex number. What is meant by complex number? Right. So then we can write many imaginary numbers, people, by using this xi form. Then for this x I can put negative real numbers like this, fractions like this, decimals like this. Many imaginary numbers you can write. Now let's see what is complex number. People, now I'm going to take this way 10 real number, 5 times I imaginary number. This is now real number, this is imaginary number. Now I can add this to 10 plus 5i, or I can subtract this to 10 minus 5i, right? This is real, this is imaginary. Here we have sum of that two, here we have difference of that two. People, this way, some more difference of a real number and an imaginary number is called as a complex number, right? Some more difference of a real number and imaginary number is called as a complex number. In other words, people, algebraic sum of a real number and an imaginary number is called as a complex number. So therefore, the most general form of a complex number, by using this definition, we can write. You can very clearly understand in this complex number 10 plus 5i or this 10 minus 5i. In forming that complex number, there are two real numbers involving in it. There are two real numbers involving in it. Here 10 plus 5 times I. Here the first real number is a real number. Therefore, in order to form a complex number, we should use two real numbers, right? So then I can write in the most general form a complex number. Suppose this simple x and simple y are two real numbers. Simple x, simple y are two real numbers. Then I can write using this y and multiplying it by I can form this way imaginary number. Okay, so I take this x here and I add them up like this. This is imaginary number, as here is 5i. This is real number, as here this 10. Then this is the general form of a complex number. These complex numbers are denoted by z letter. Z equals x plus iy. This is the usual practice to denote this kind of complex number. We use the letter z. Z letter stands for the complex number, right? So therefore, the general complex number we can write z equals x plus iy. Remember, both these x and y are real numbers. Okay, are real numbers. And you can very clearly understand, therefore, there are two parts in a complex number. This part and this part. This x and this y, both are real numbers. But when we write this way in the complex number, this x we call as, x is called as the real part of the complex number z. X is called as the real part of complex number z. Real part of the complex number z. It is written like this, REZ. Real part of the complex number z. Okay. And this y, this y is a real number. But that y really participating there to form the imaginary number of the complex number. This complex number has two parts now, a real number and imaginary number. Y is real, but that is involving to represent the imaginary number of the complex number. Then this y is called as the imaginary part of the complex number z. Imaginary part. Imaginary part. Imaginary part of the complex number z. It is written like this. Im z. Imaginary part of the complex number z. Im z equals y. Imaginary part of complex number z. But remember this, both x and y are real numbers. Both x and y are real numbers. Right. Now, the other thing. Here now, when I consider this way, if I need to write complex number, the most general form of the complex number is this. This x and y both are real numbers, right? Okay. Now, I am going to put for this x real numbers taken from the set of real numbers and keeping always this y at 0. Y can be any real number, no? For this y, I supposed to put 0 always. Okay. And now, given for this x, different real numbers taken from set of real numbers, right? I am going to form some complex numbers. Now, for example, I am going to put x equals 1, y 0. Then y 0 means 0 into I. That product is 0. When you multiply anything by 0, the answer is 0, no? Then the complex number we get for x, we have to put 1, right? So then the complex number is z. I'll take that complex number as z1, right? Secondly, I put for this x 0.5 and y 0. Then the second complex number we get is z2, 0.5 plus 0. We get z2 complex number as 0.5. I put x equals minus 0.1 and y 0. Right, people? Then we get z2 3 as minus 0.1 like this. People, all these Z1, Z2, Z3 are complex numbers. They are complex numbers, right? But once you very carefully look at these complex numbers, those complex numbers are nothing but, people, they are real numbers. See on the right hand side of this complex number, 1 we have, it's a real number. And 0.5 also real number. Minus 0.1 also real number. So this way, people, we can very easily say what? All the real numbers in this way, since this x is a real number, no, keeping this y at 0, we put all the real numbers for the place of x. Then we can generate infinitely many complex numbers. But all those complex numbers, you can see what, people? Real numbers. This says what? All complex numbers or all real numbers. All real numbers are what? Complex numbers. That means any real number, people, any real number is a complex number. Any real number is a complex number according to this logic. That means, people, we say what? We know set of real numbers we learned at the very beginning of the in your school, and I also did, I think, in the class, right? We learned at the very beginning set of real numbers like this. That occasion, we said, of course, this set of real numbers is the biggest set which contains elements. But, people, no longer that is true. Okay, no longer that is true. By putting this way, y values also without 0, some other values for this y, for x and y, right? We can generate complex numbers. Suppose substituting for all real numbers for x and all real numbers for y, we form all possible complex numbers. And all those complex numbers I am going to put into a set like this. Then what is this set? This is the set of complex numbers denoted by C. In that set, people, in a very limited area only, that what? Complex numbers which are purely real available. So therefore, this R is actually inside this C in a small place. So this says, people, here in this place, all the complex numbers are real numbers. On outside of that, people, we have what? Complex numbers which are not real. So therefore, the biggest set of numbers no longer is this R. The biggest set of numbers is the set of complex numbers. Set of complex numbers. Understand? So therefore, in this case, people, remember, if any result is true for complex number, is equally true for what? This real number. In the future, in this lesson, people, we derive some results, properties of complex numbers. Okay. Those all properties equally valid for what? Real numbers, because any real number is a complex number. Understand? Okay. All right. So that you have to understand as the next part. And the other thing, people, now we can form complex numbers by using this common x plus iy form, right? That is a standard way of writing any complex number. Now, people, you can, right? As I told just now, the imaginary part, y is called as imaginary part now, people. Imaginary part of z is this y, right? We set this y to 0. That means putting this y 0, I'm going to obtain the complex numbers. Then in that complex number, people, you can see, since y is 0, x plus 0 we have z is 6. Then we can very clearly see on the right hand side, we have a real number. That means when the imaginary part is 0, the resulting complex number is people a real number. That occasion, this complex number Z is called as Z is purely real. Z is purely real. Complex number Z is purely real. So then what is meant by purely real? In a complex number, if the imaginary part, people, imaginary part is only this y, not I, y both. Not I, y both. Only this y is called as the imaginary part. If this imaginary part of the complex number is 0, the resulting complex number contains on its right hand side a real number. Therefore, that occasion, the complex number is called as purely real. So therefore, a complex number becomes purely real if its imaginary part is 0. Right. Now the other thing is, we put people x0. X means what? Real part of Z. It is x. We put this x0, right? Real part. When you put 0, people, x is 0, no, right? When x is 0, we get Z is IY. Z is IY. Then you can very clearly understand the complex number is on the right hand side, we have imaginary number. Right? On the right hand side of the complex number, Z is imaginary number. So then in this case, we see what the complex number is purely imaginary. Z is purely imaginary. Therefore, Z is purely imaginary. Therefore, people, a complex number becomes purely imaginary complex number when its real part is 0. When its real part is 0. Right? Okay, those things at the very beginning you must understand. Right. And the other thing is some properties of the complex number, right? We define this a conjugate complex number. Conjugate complex number of a complex number. We have conjugate. Suppose Z is x plus IY is a complex number where this x and y are real numbers, right? X comma y are real numbers. Now, of this imaginary number, this IY is imaginary number now, people. Its sign we change to opposite, like this. Then this one is called as the conjugate of Z complex number and denoted by Z bar. Then the conjugate complex number is obtained how? By changing the sign of the imaginary number available in the complex number to opposite. That means before this I, the sign we change to opposite. Then the resulting one is called as the conjugate complex number of this complex number. Conjugate Z bar. That is how we define the conjugate complex number. Another one we define as modulus of the complex number. Modulus of a complex number. People, when I consider this one, Z equals x plus IY, the modulus of this complex number is defined to be Z mod is equal to square root of x squared plus y squared. Modulus of Z is equal to x squared plus y squared. What is this x, people? X is the real part of Z. What is this y? Imaginary part of Z. So therefore, modulus of the complex number Z is really perfect squared of the real part of Z plus perfect squared of the imaginary part of Z. Root. This is how we define the modulus of a complex number. Real part perfect squared plus imaginary part perfect squared root. is called as people modulus of the complex number z equals x plus iy, right? Okay, this is some theories, some definitions people we have, right? So there are many definitions. Based on these definitions, there are some theories. So therefore, this lesson contains more theories, people, right? If you can remember these theories and definitions, then only you can work out questions. So therefore, next day lesson, before coming to the class, go through this all what definitions and important theories today we learn. You have to practice and join the class. Then, of course, very easily you can understand the things. Otherwise, it is confusing if you can't remember the definitions and everything, right? This lesson is highly based on what? Definitions. Okay, right. So then people will come to a brief note regarding these things so far we learned, and thereafter we'll go for the next definitions, right? Okay. Then write down people heading as complex number. Then it's subheading write down as imaginary numbers. Imaginary numbers. Imaginary numbers. Right. Write down subheading as imaginary numbers. Right. Okay. Now we'll write down people a note. Write down if the perfect square of a number is a negative real number, then the number which has been squared. Then the number which has been squared. Is called as an imaginary number. An imaginary number. See this one. When we get what? -4 half n 2. Simplify this. You see. Then we get -4 square root of -4. Square root of -4 square is -4. Then people, this part is what? An imaginary number. Imaginary number. Then we can write many examples for imaginary numbers. square root of minus 3, square root of minus 2, square root of minus 9, and so on, people. We can write infinitely many imaginary numbers. Infinitely many imaginary numbers like this. Right. Right, now people we can write next subheading as imaginary unit. Imaginary unit denoted by I. Imaginary unit denoted by I. Right. Write down people like this. The imaginary unit within bracket I is defined so that I squared equals minus 1 or I equals square root of minus 1. I squared equals minus 1 or I equals square root of minus 1. Right. Write down people like this. Now consider the imaginary number. Now consider the imaginary number square root of minus 4. Square root of minus 4. We can now write these people like this. Minus 4 I can write minus 1 into 4. Okay. I can write minus 1 as I squared into 4. Yes. In 4 I can write people its root plus or minus 2. I square root is I know. See we get. Right. This way when I write this imaginary number, you can very clearly see any imaginary number you can write. There are two answers for this now. 2i, 4. This imaginary number you can write in two ways on the right hand side as 2i and minus 2i. Then you can see this imaginary number you can write as real number multiplied by the imaginary unit. Okay, now come up to there and then we'll write like this. Write down. By this we can say an imaginary number an imaginary number can be written as an imaginary number can be written as a product of a real number, and the imaginary unit, product of a real number and the imaginary unit. That is, when simple x is a real number, xi denotes or xi gives an imaginary number. Imaginary number. Therefore, people, we can write any more examples for imaginary numbers. Examples: 2i minus half I, 0.2i, minus 1/3 I, so on. Infinitely many imaginary numbers now we can write. Right now. Right now, people come to next one. Complex numbers. Complex number. Complex number. Right. We'll write people under that. Write down like this. The sum, SUM, the sum or difference. The sum or difference. The sum or difference of a real number and an imaginary number. Of a real number and an imaginary number. The sum or difference of a real number and an imaginary number is defined as a complex number. Is defined as a complex number. Now write down, let x comma y be any two real numbers. Any two real numbers. Then z equals x plus iy. Z equals x plus iy. Gives a complex number. Use a complex number. We use people Z, the notation Z, to denote complex numbers. To denote the complex numbers. Right. And you can write there Z equals x plus iy. X, y both are real numbers. Then here x is called as a real part of Z. Real part of Z. Real part of Z. It's written like this. It is x. Next one, imaginary part. Written as IMZ. This is y. Imaginary part of Z, IMZ equals y. Right. Now this y is 0. That means imaginary part of Z 0. Then for the complex number Z, we get only x. That right hand side we have a real number. Then the complex number is called as what? Purely real. If x is 0, then right hand side we have iy. Then right hand side we have imaginary number. Then the complex number is called as purely imaginary. Then write like this, people. If the imaginary part of the complex number is 0, write down that is y0. The complex number is Z equals x. That is y equals 0. Complex number is Z equals x. Write down. Then the complex number is called as purely real complex number. Purely real. Purely real complex number. Now write down. If the real part of the complex number is 0, if the real part of the complex number is 0, if the real part of the complex number is 0, if the real part of the complex number is 0, that is x equals 0. Complex number becomes now people iy. Complex number Z becomes iy. Write down. Then the complex number is called as purely imaginary. The complex number is called as purely imaginary. Purely imaginary. Right. Right now, people will come to the next things. Conjugate. Complex number. Of a complex number. Conjugate complex number of a complex number. Right. We'll consider people a complex number Z x plus iy, where both is x and y are real numbers. Both is x and y are real numbers. Right? Then the conjugate of Z. Conjugate of Z is denoted by Z bar. Z bar is defined as Z bar is equal, people, the sign before this I, we have to take opposite, x minus iy. This is how we define the conjugate complex number of a complex number. Z bar equals x minus iy. Right? Right. Next one, people. Modulus of a complex number. Modulus of a complex number. We'll write lit. So d equals x plus iy, x, y both are real numbers. Then write down. The modulus of the complex number Z is denoted by mod Z and is defined as mod Z equals square root of x squared plus y squared. X is real part of Z perfect square plus y means imaginary part of Z perfect square. What is it? Modulus of Z is this. Right now, people? Yeah. Then you can very clearly understand Mod z is positive real number. You look at this. Mod z is right hand side before the root sign we have positive sign. No? Then mod z is what people? Positive real number. Positive real number. Because x is real number, then x squared is positive value. Y is a real number. Its perfect square is positive. If both x and y are 0, then right hand side 0. Therefore, the complex number, modulus of a complex number is either 0 or positive value always, right? 0 or positive value, right? A real number. Modulus of a complex number is always a positive real number or 0, right? Now, next one, people. We define another complex number called as inverse of a complex number. Inverse of a complex number. Write down like this. Write down inverse complex number. Inverse complex number of a complex number. Right. People, here, you have to very carefully understand the inverse complex number. Just understand this inverse complex number. Now, you know, people, when I multiply 5 by 5 to the power minus 1, here 5 to the power minus 1, the answer is 1. How? This 5 to the power minus 1 I can write as 1 upon 5 like this. Simplifying this, we get 1. Then this 5 is a real number. Real number is a complex number. And 5 to the power minus 1 is also, people, real number. 1 upon 5? No. 1 upon 5. 5 to the power minus 1 is 1 upon 5. 1 upon 5 is a real number. Real number is a complex number. Then, people, then this one, okay, is called as inverse of the complex number this. That means if we take a complex number z, we multiply this complex number by another complex number. Then suppose the answer is 1. Then the complex number here we have is called as z inverse and denoted by this way. People, you have to understand, in this case, we use the word z inverse. Z inverse. Z inverse. Okay. Really, in this case, this inverse means, people, z to the power minus 1. Z to the power minus 1. For the power minus 1 only, in this case, we use the word inverse. Because this is very important, we have used the word inverse in other 2 places in our pure maths. What are those 2 places? In trigonometric functions. You know, sine inverse we have used. Sine inverse 1. People, sine inverse 1 is, you know, pi by 2, no? Or when you write like this, sine pi by 2, it is 1, no? Then in this case, when we need to subject this pi by 2, we take the sine to right hand side and we write it as sine inverse. There we use the word inverse. And people, the other one, we use the matrices, no? There also we learned, if A is a matrix, then we say they are A inverse matrix, inverse matrix of a matrix. There are, people, the notation here minus 1, here also minus 1. They are really inverse. But here also, for this z, we use minus 1 and called as inverse. People, in this case, this inverse mean, and here the inverse means being two different. Understand? So this confusion, of course, last Friday I did this lesson to the Friday group. I tried to explain this one anyway by confusing. I stopped the explanation there. You have to very carefully understand. Here is inverse means -1 power. Understand? You know, we can't write people. We can't write this thing. Can you write sine inverse 1 as 1 upon sine inverse 1? No, because here this -1 is not the power of this sign. That is called as the inverse. People, can we write matrix, inverse matrix of A as 1 upon A, taking this denominator? No. Why? Because though this is -1 we have, that is not a power. That is called as the inverse. Right, people? You know, we can't divide 1 by a matrix. No, that has no meaning. But people, here, though we use the word inverse for this -1, here this z to the power -1 is, people, right? Z to the power -1. That inverse means z to the power -1. Z to the power -1. Here this, though we use the word inverse, that -1 is power -1. Okay. That can be, since it is a power, you can write this as 1 upon z. Okay. So therefore, for a complex number, its inverse we can write as 1 upon z, because this -1 is the power. Right? But I tried to explain, in all the cases for inverse, right? For all inverses, you can't write like this. For all, not for the complex numbers. I said in commonly. For all inverses, commonly for all inverses, this way you can't write. The example is this. If A is a matrix, A inverse you can't write as 1 upon A. This is wrong. Sine inverse 1, you can't write it like this. I tried to give the idea that for all inverses, this way you can't write. Is an inverse 1, is an inverse, that is to the power -1. We can write as 1 upon z, because here the inverse means the power -1. But here inverse means not the power. Then I commonly, of course, said for all inverses, you can't write like this. For all inverses. For the case of complex number, possible. But for the cases of this and this, you know, we can't write like this. So therefore, in this case, we have to very carefully understand, though we use the word inverse to give inverse complex number, they are the inverse mean people. For the case of complex number, inverse means the power -1. Understand? Okay. But here, and here the inverse means not people, power -1. They can't be written like this. That only by writing, using the z letter I wrote there. Then of course I'll stop explanation, because that occasion the student confused that. But you have to very carefully understand, though we use the word inverse, right? Here the meaning of the inverse, and at these two places the meaning of the inverse being different. Here the meaning of inverse means power -1. But at these places, people, inverse means not power -1. They can't be written down like this shown on the right hand side. So therefore, the case of complex number inverse, it is, we have to understand as power -1. Therefore, you can write as this way, and we can prove that also. Okay. Yeah. Now, people, we define the inverse complex number like that. When a complex number is multiplied by another complex number, if the answer is 1, then this second complex number is called as the inverse of the first complex number and denoted by this symbol. That is how we, right, define the inverse. And sometimes this is called as the multiplicative inverse. multiplicative inverse, right? Okay, so then we'll take down that one. So therefore, carefully understand this situation, right? Right. All right, like this. Let Z, let Z B, let Z be a complex number let Z be a complex number, then inverse of Z is denoted by Z inverse and defined such that also that so that Z into Z inverse equals 1. Z into Z inverse equals 1. Right, people? Write down. The inverse complex number of Z the inverse complex number of Z that is Z inverse is given by Z conjugate divided by mod Z squared. Z conjugate divided by mod Z squared. Right? We'll prove this later, people. We'll prove this later. Right? We come to this later, right? Z conjugate divided by mod Z squared. Right? Now people will write next subheading. Write down like this subheading: addition, subtraction, multiplication, and division of two complex numbers. Of two complex numbers. Right, people, we'll come to this. Try to like this. Let Z1 x1 plus iy1 and z2 x2 plus iy2 b two complex numbers where x1 y1 x2 y2 are real numbers. Fine. Now people, first one, addition. I'll take people like this. Z1 plus Z2. These two complex numbers I'm going to add. Z1 is x1 plus iy1 plus Z2 x2 plus iy2. Then you can take this x1 and this x2 together like this and take this y1 plus y2. The left hand side people, we have Z1 plus Z2, right? You know this x1 and x2 are two real numbers, people. Then their sum is another real number. y1 and y2 are two real numbers. Their sum is another real number. Then I'm going to take this as x. Let capital X is x1 plus x2. It is a real number. Capital Y, y1 plus y2. That's also a real number. Then this z1 plus z2, we can write x plus iy, where x, y both are real numbers. Then what can you say, people? z1 plus z2, sum of two complex numbers, takes the form like this here, x plus iy, both x and y are real numbers. So therefore, sum of two complex numbers will give as the result another complex number, right? So sum of two complex numbers is another complex number, right? I'll write down. Therefore, sum of two. Therefore, the sum of two complex numbers. Therefore, the sum of two complex numbers. Therefore, the sum of two complex numbers is a complex number. Is a complex number. Right. Now we will take second one, difference, or the subtraction means difference. Right. Take Z1 minus Z2, number 2. Subtraction. Now you can see the subtraction Z1 minus Z2. In the same way, people, you can simplify. Show that also another complex number. Right, people, now when you take the difference, right, here we get the subtraction number 2. Here we get minus sign, here we get minus sign, right? Then here we get minus, here we get minus, right? This is minus, this minus, right? Then you can write again this Z1 minus Z2, the difference of two complex numbers again become a complex number like this. Therefore, difference difference of two complex numbers is a complex number. Is a complex number, right? So therefore, when we add two complex numbers, people, the result is a complex number. When you take difference of two complex number, is people complex number. Right. Now the multiplication will take third one. Take the third one as the multiplication, right? Multiplication. Multiplication. number 3, right? Z1 into Z2. Z1 multiplied by Z2. Z1 is x1 plus iy1, x2 plus iy2. Right, so then what do you get? You can multiply these two, we get x1, x2, and people, these two, I and I squared, y1, y2. And next one, this x1 with this y2, take I out, x1, y2, and next one, people, this iy1, x2, then take I out, x2, y1. You know, people, this y squared, I squared, this is minus 1. Then I can write z1, z2, x1, x2, plus and minus make minus y1, y2, plus I times this x1, y2 plus x2, y1, right? All right. You know, people, x1, x2 are two real numbers. Therefore, their product is another real number. Similarly, this product is a real number. Difference of two real numbers is a real number. So therefore, this is a real number. Suppose this takes x. X is a real number. This also, in the same way, we can say, people, this should be a real number. Suppose y. Then z1, z2 product will be of the form z1, z2 product will be x plus iy form, where x, y both are people real numbers. Therefore, what can you say? The product of two complex numbers is another complex number. And then write down, therefore, the product of two complex numbers is a complex number. Is a complex number. Right. Finally, we'll take, people, the division, fourth one. Division. Z1 divided by Z2, say x1 plus iy1 divided by x2 plus iy2. Right? Yeah. People, remember, whenever we need to divide, two complex numbers, this division we do usually this way. Z1 divided by Z2, no? Right. x1 plus iy1 divided by x2 plus iy2. When we divide two complex numbers, people, remember, the division is done how? Multiplying both this numerator and denominator by the conjugate of the denominator. By the conjugate of the denominator, we multiply both numerator and denominator. So then this we have to multiply by the conjugate of the denominator. Conjugate of the denominator, you know, x2 minus iy2. Right. Okay. Now, People now simplify this 2, you have to multiply, this 2 you have to multiply, and then show the division also another complex number. The division also another complex number. Right. All right, so then people, I can simplify here. Z1 divided by Z2. You can think here this as A, or this as B. Then here we have A plus B. This is A minus B. A plus B, A minus B. Then their product is what? A squared minus B squared. Therefore, square of this minus square of this. X2 squared minus IY2 squared. Now here you can multiply x1, x2. This and this I can multiply. I and I squared, it's minus 1, and this minus sign is plus y1, y2. Then I multiply this and this, take this I out, x2, y1, and this minus x1, y2. Right. Then here we get people I squared, it's minus 1, that minus, and this make plus. Then we get Z1 divided by Z2, x1, x2 plus y1, y2, I times this. Here this is x2 squared plus y2 squared. That is we get, right? Now people, you can very clearly understand here. x1, x2, y1, y2 are 4 real numbers. Then this is numerator is a real number, denominator is a real number. Division of 2 real numbers is another real number. So therefore, if I take this as x, capital X, it's a real number. This is capital Y, it's a real number, right? So therefore, this division also, people, a real number. Z1 divided by Z2, x plus IY. X comma Y real numbers. So therefore, division of 2 complex numbers is, people, another complex number. Write down that. Write down. Division of 2 complex numbers. Division of 2 complex numbers is another complex number. Right. Right, people, now we can come to the, that is a inverse proof. You can consider it like this. As a note, you can now write, let Z equals x plus IY, where xy both are real numbers. Then you can write, people, Z bar x minus IY mod z root of this. Now people, you can very clearly understand, when I take Z into Z bar divided by mod z squared. I write Z multiplied by z multiplied by z bar divided by mod z squared. Even now this z bar is a complex number. Mod z square is a real number, no? Real number is also a what? Complex number. Then this is a complex number. This is a complex number. Division of two complex numbers, just now we proved as a complex number. So therefore, Z is a complex number given. This is also a complex number. Now I am going to find out the answer of this. Then Z is this x plus iy, right? And Z bar going to be x minus iy. People, mod z squared means x squared plus y squared. So what do we have here? A plus b into a minus b. That is a squared minus b squared. No? Then x squared minus iy squared. You know, I squared is people minus 1, that minus and this minus make plus. Then we get to the numerator x squared plus y squared divided by x squared plus y squared. Then here we have z times z bar divided by mod z squared. I take this as a separate complex number like this. So you know, after cancelling this and this, we get 1. Then z is a complex number multiplied by this. One. So now we said this is a complex number. When it is multiplied with this z, the answer is 1. According to the definition of inverse complex number, people, when this z is multiplied by this, since the answer is 1, this should be the inverse of this complex number z. So clear? Right? So therefore, this should be the inverse, right? Inverse complex number is that. Right? Therefore, you can write Z inverse should be this Z bar divided by mod Z squared. This is Z inverse. Right? Right. Now let's see. Next one like this. People, I am going to write 1 upon Z. Now, 1 upon Z. People, 1 is a complex number. 1 is a real number, no? We said n real number is a complex number, no? Z is a complex number. Then here we can consider this 1 upon Z as what, people? Division of two complex numbers. Division of two complex number results another complex number. So this is another complex number. Let's see what is the answer. I told you people this way, when we need to divide two complex numbers, the division is of course done multiplying both numerator and denominator by the conjugate of the denominator. Conjugate of denominator, the denominator is z, then z bar. By z bar we multiply numerator and denominator. Okay. You can very clearly understand this z bar divided by this one, x plus iy into x minus iy is the conjugate. Then you can very clearly understand z bar divided by this is a plus b into a minus b. What is that? A squared minus b squared, no? Right? Z bar. Therefore, here x squared, I squared is people minus 1 with this minus and plus 1, y squared. This is what we get. But you know this one, x squared plus y squared, it is nothing but when you square this one, mod z squared is x squared plus y squared. Right? So therefore, we get 1 upon z is now z bar divided by 1 z cat. Right? Now, people, can you see something? This one and this one being the same. Therefore, z inverse is equal to 1 upon z. Therefore, z inverse is equal to 1 upon z. Okay. People, now this is the place most of the time the student get confused. We use the word here inverse, no? Z inverse is equal to 1 upon z. Right? Then inverse you can write as 1 upon. Then people, using this way, z inverse is 1 upon z. Z inverse is equal to 1 upon z. Getting this as true for all situations, if you apply this for matrices, say here, A inverse should be able to written as 1 upon A. This is completely wrong because we don't define division of two matrices. Understand, people? So therefore, you have to very carefully understand for all the situations, right? Inverse, we can't write like this. Only for the complex number, this way, inverse we can write z inverse as 1 upon z. Here, really, this inverse means, people, power minus 1. For this power minus 1, only the word inverse we use. Okay, that thing you have to very carefully understand. Sometimes this property inverse we can write 1 upon this way, maybe sometimes applying for this way, people, tan inverse rule 3, then might be writing like this. This is wrong, people. That is why I in general said what inverse, for inverse cases, for all cases, inverse we can't write like this. Z inverse equals 1 upon z is true when z is a, people, complex number. But when z is what? A matrix, then A inverse you can't write as matrix inverse, you can't write as 1 upon matrix. That's wrong. That idea you have to get very clearly. Okay. Then here, remember, people, this inverse mean power minus 1. That's very important one. This only the people get confused in the last class, but that is really nothing confusion. You can very clearly understand, right? So in this case, z inverse is equal to 1 upon z. Here, though we use the word inverse, the inverse means power minus 1. That way, when you keep remember, you can avoid the confusion, right? Now, people, we can go to the next part. I'll write down this one and you can go to the next part. I'll write down next one as equality of two complex numbers. Next subheading, we can write equality of two complex numbers. Equality of two complex numbers. Right? Right, people, now let's see what are the conditions required for two complex numbers to be equal. Right. Thereby, we can get some more results. Right? Yeah. You can write now like this. Let z1 x1 plus iy1 and z2 x2 plus iy2, where what are these? X1, x2, y1, y2. They are 4 real numbers. They are 4 real numbers. They are 4 real numbers. Right. Now, people, I'm going to write this way, let Z1 is equal to Z2. Z1 is equal to Z2. Z1 is equal to Z2. Now I substitute for Z1. X1 plus IY1, Z2, X2 plus IY2. I take this X2 to this side, minus X2, IY1 to right hand side, take I out, Y2 minus Y1. Now people square both sides. Square in both sides. What do you get? When you square both sides, you get people x1 minus x2 perfect square plus equals I squared times y2 minus y1 perfect square. Well, this I squared is minus 1. Then you can bring this to this side. It is now plus, no, once you bring this to this side, plus y2 minus y1 perfect square. Now on the right hand side we have 0. This difference you can interchange the order. Y1 minus y2 perfect square equals 0, like this. Okay. Now we will this x1 and x2 are two real numbers. Then x1 minus x2 is a real number. This bracket is real number. Its perfect square is either positive or 0. You know, perfect square of any real number is positive or 0. Like that, this also positive or 0, this whole thing. Sum of these two equals 0 mean this value 0 or this value 0. Okay. Otherwise, there's no chance of occurring this. And this implies therefore people what? X1 minus x2 equals 0 and y1 minus y2 is equal to 0. This gives us people x1 is equal to x2 and y1 is equal to y2. What do you understand by that, people? The real parts of the complex numbers should be equal, and what? Imaginary part of the complex numbers should be equal. Okay. Right. Therefore, the condition required for two complex numbers to be equal are what, people? The real parts of them should be equal, and the imaginary part of them should be separately equal. Okay. Real parts and imaginary part should be equal separately. Then only we see that two complex numbers are equal complex numbers. Okay, right. Then come up to this first, and then we'll write in sentence. Write down like this. Write down therefore, two complex numbers become equal if their real parts equal and imaginary parts equal. Imaginary parts equal. Right. Okay, now we can go to one question, people. Right. Question is this. If x plus iy is equal to 1 upon a plus ib. Then show that a squared plus b squared into x squared plus y squared equals 1. Right? Okay. Now I'll take this one now. X plus iy is equal to this, right? Now this right hand side, to simplify this, what I do is, people, I multiply the numerator and denominator both by the conjugate of the denominator. Then we get x plus iy is equal to, conjugate of this is going to be a minus ib divided by a plus ib into a minus ib. Now keep simplifying this, people. Then the denominator you can simplify. It's like x plus y into x minus y. So therefore, the denominator on the right hand side we can write as x squared minus y squared, right? Right, here we have product of the factors of difference of 2 squared. So then we can write that as a difference of 2 squared. It is a squared minus ib perfect squared. You see minus ib. Yeah, I squared is minus 1, that minus and this make plus, here b squared, right? Here a squared plus b squared. We get x plus iy, people. A divided by a squared plus b squared. Here plus I minus b a squared plus b squared. Now, people, what do we have? We have on the left hand side the complex number. Right hand side also we have a complex number. Now this time we have two complex numbers are equal. Two complex numbers are equal. Right? You know, when two complex numbers are equal, the real parts should be equal and imaginary part should be equal. Right? So therefore this implies what? X equals this a upon a squared plus b squared. Y equals minus b upon a squared plus b squared. But we need to show this. What I do is this. I write x squared plus y squared, and for this x I substitute by this, for y we substitute by this. A divided by a squared plus b squared perfect squared plus y squared, means people minus b, this. Now you can simplify this and you get the answer. So then here what do you get? A squared upon a squared plus b squared perfect squared plus b squared upon a squared plus b squared perfect squared. Then you can write this as how? the denominators are equal, no? Then you can write like this. This and this you can cancel down. You get this. Left hand side we have x squared plus y squared like this. Then use the cross multiplication and get the first answer. Equals 1. Here's how we take that answer. Right now, right. Next question people write down. Find the square root of 2y. Find the square root of 2y. Find the square root of 2y. But people here, this square root of 2y. This no? We need to find. We assume it forms as. Here now, when you write this, say square root of 4. It's true, no? Here this is a real number, its root. Real number is a complex number. Its root is what, people? Again, is 2. 2 is a real number. Real number is a complex number. People, what if I write this answer 2 like this? And this left hand side is 4. 4 plus 0y. Can you get an idea? But this is a complex number. Its root is another complex number. Like that, people, here 2y. Its real part is 0. This is a complex number. Then its root is, people, another complex number. So therefore, I am going to assume for the square root of 2y as a complex number like x plus iy. Root 2y, I am going to assume as x plus iy. If you can find this x and y, then we know the square root of 2y. Then people, what we do? We will square both sides. Then we get 2y x plus iy perfect square. Then get square is x squared 2x y times iy squared 2y. Yeah, I squared is people minus 1, x squared minus y squared. Yeah, I times 2xy. Left hand side we have 2y means 0 plus 2y. You can write this and this, you can equate. Real part must be equal, no people? X squared, y squared, difference should be equal to 0. Real parts are equated. This gives us an imaginary part. 2xy should be equal to 2. This and this you can cancel down. Xy equals 1. And this gives us, people, x squared, y squared equal. Now there are two equations. By these two equations, people, solving, you have to find x and y both. You have to find x and y both. So then what do you get? Here, by 2, you can subject y as 1 upon x. Put that in number 1. Put in number 1, we get what? X squared is equal to, right? Y is, people, 1 upon x squared, no, this. Bring this here, x4 equals 1, x is plus or minus 1. People, x is a real number, right? X is a real number because xy, right, available we are in the complex number here. Complex number here. There this xy are real. Right. And then x has two answers, no? X equals plus 1, x equals minus 1. For the x plus 1, what is the relation between x and y? Y equals 1 upon x. Then when you put, here we get y1, here y minus 1. Then, people, we know two values for x we have, two values for y we have. Then for the square root of 2y, people, there are two answers. There are two answers. So therefore you can write square root of 2y. When I take first set this 1 plus I, second set if I take, right, minus 1 minus I. This is minus 1 plus I. Therefore you can write square root of 2y, the two answers taken together, as plus or minus 1 plus I. Correct, no? Here plus, here minus. This is how we take that answer. Right. Okay, people, now we'll come to the next part. Right, then write down next one as the modulus of I. Modulus of I. I is the imaginary unit. I is the imaginary unit. Right. People, this I is also a complex number. How? This I, we can write this way, no, people. 0 plus 1, 9. No. I equals 0 plus 1, 9. That way you can write. 0 and this 1, both are real numbers. Therefore, this right hand side, this is a complex number. Since it is equal to I is a complex number. Then you can write let Z equals I. I is 0 plus 1, 9. Then people, mod Z is really square root of real part squared plus imaginary part squared. Then what is that is equal to, this is 1, right? You know, people, Z is what? Here, I. Put this I here. Mod I is 1. Modulus of I is 1. Modulus of I is 1. Right, no? Okay. Now, next part is when we need to multiply a complex number by a value. When we need to multiply a complex number by a value. Right. Now, for example, suppose we have a complex number like this. Z equals 2 plus 3i. Real part is 2, imaginary part is 3. Well, now suppose we need to multiply this complex number Z by 2. Then how to multiply this, right? Left hand side and right hand side, both we multiply like this. Then the real part and the imaginary part, we have to multiply. This way, we get the 2Z complex number. And like that, when you multiply this by minus 1, then what do you get? Minus Z complex number coming. Right hand side minus 2, minus 3i. Minus 2, minus 3i. That way we get the minus Z complex number. Okay, now then write down the next subheading like this: multiplication of a complex number. Multiplication of a complex number. Multiplication of a complex number by a real number. By a real number. Right. By a real number. Now write down people like this. Let Z equals x plus iy, x comma y real numbers, write down. Let Z equals x plus iy, semicolon, x comma y belongs to set of real numbers. B, a complex number. Be a complex number. I don't let lambda be a real number. Lambda be a real number. Then lambda Z equals lambda times x plus iy, and result equals lambda x plus I times lambda y. Lambda x plus I times lambda y. Now we can write when lambda equals -1, when lambda equals -1, we get minus z complex number equals -6. Here when you take -1 here, we get minus iy, -x minus iy. Right. Okay, now people. Right, now we have some proofs, people, to do. Those proofs are very important proof. In every past paper, when you go through this, among these proofs we do, some of them available in every past paper to prove. Right, so therefore these proofs, of course, in general we do every year, because some of them definitely come into prove at the examination. Right, okay. Write down some heading there as history. Some important proofs is the next subheading. They are here, right? Some important results. Some important results. First one, write down. Is it Baba? Is it Baba? Is it? Is it Baba? Is it? Number 2. Z plus Z bar. 2 times of real Z. Z minus Z bar. 2 times I am Z, major part of Z. Number 4, people. Mod Z greater than or equal to real part of Z. Some more results available. First do this 4. Some more available. Right. We'll see to prove each one. One after the other, right? Right. People, these results you should know how to prove. And you should remember these results. Because whenever we work out question, most of the time, very often, right, we use this result. Right, okay. Right, come to the proof. Proof is this. First one, we take let Z equals x plus iy. What can say people? Then real part of z is x and the major part of z is y. Then we get number 1 z bar going to be people x minus iy, no, right? Then of this z bar I take another conjugate. The conjugate of this going to be, take a sign this to opposite, x plus iy. This is nothing but this, it is z. Z bar is z. Z conjugate, its conjugate, z bar is z. Okay, no people. First one is okay. Second one, z plus z bar. Here, z these people x plus iy, z bar x minus iy. These two you can cancel down. X and x we get 2x. Z plus z bar. But what is that x people? X is the real part of z. Then 2 times real part of z. That one, okay. Number 3, z minus z bar. X plus iy minus z bar, x minus iy. These two you can cancel down. Iy minus plus iy, we get 2iy. As in the left hand side, z minus z bar. Then we get z minus z bar as 2i times y is imz. Right. People, the fourth one. You know mod z. How to write mod z? It is x squared plus y squared. Right, no? Right. We have to prove the mod z greater than or equal to real z. Right. You can very clearly understand people this way. Here is this. X squared plus y squared root. You can write this, you know, people. Greater than or equal to this way. I write. This is correct. Even this x and y, two real numbers, no? If this y is 0, what do you get? We have x squared inside root sign, x squared root. It is equal to what, people? The right hand side, this equal sign becomes valid. If y has particular answer value, then this left hand side greater than this part. Now, for example, if I take like this, think like this, 3 squared. Now, suppose x is 3, y, I take 4, 3 squared plus 4 squared. What is this, people? This is 5 now. Now, if I write this way, 3 squared plus, here people, once we have 0, this answer, what can you say? This answer is equal to what? This, no? The equal sign become valid. If I put instead of this 0, people, suppose 1. Now, what can you say about this value? This is obviously greater than this, no? Because for this 3 squared, something added and taken the root. That answer should be greater than the previous answer. Okay? So therefore, people, I can write it like this. Okay? People, we get here x squared root. Think like this. 5 squared root. Here, obviously, we have taken positive, no, people? Positive square root. This answer is plus 5. Okay? Right. Answer is plus 5. And can you remember this one? Modulus of x. X is a real number. Greater than or equal to just x. Why? Suppose this way. X equals minus 5. Put in the left hand side minus 5 modulus. Right hand side minus 5. Minus 5 modulus is 5. Right hand side minus 5. Which is greater? This is greater. This sign becomes valid. Suppose x is plus 5. Now put here 5 modulus. Right hand side 5. 5 modulus is 5. Right hand side is 5. Now these two are equal. Therefore, people, you can say this way. When x is a real number, mod is greater than or equal to x. Now I can write this way. People, this one I can write. This way, mod x. The reason why. X can be positive or negative. This one now. After squaring that, we get definitely a positive value. Then when I take the square root, this positive square root we have taken, then this answer should be positive. Final answer should be positive. But I am going to write that answer as x. This x. But we don't know whether this x is positive or negative. X, suppose x is minus 5. Minus 5 squared plus 25. Its root is plus 5. Then to the right hand side we get plus answer. So therefore, we have to put modulus here. Then I can write this thing like this. X squared plus y squared root greater than or equal to mod x. Right. But mod x greater than or equal to x. Okay. Therefore, we can write, people, this implies root x squared plus y squared greater than or equal to x. What is x? X is a real part of z. What is this root x squared plus y squared? Mod z. This is mod z. Mod z greater than or equal to x means real part of z. right? Like this, we get. There's nothing to confuse there, people. We can write x square plus y square root greater than or equal to 1 x greater than or equal to x. This x and y are real numbers. This is greater than this or equal to this, greater than or equal to this. Therefore, this and this we can write like this. Then we get this. Right. So then this is how we do that. Right, people, any question here in understanding this? Right, no? Right, that is the first set of proof. Right. People, the next parts will continue next day.